Think about where you're sitting right now. The building around you, the road you took this morning, they all share one massive common denominator. Humanity pours so much concrete that it sits exactly behind water as the second most consumed resource on Earth. But the foundation we've built our modern world on has a major flaw. It is entirely mute. Concrete bears unimaginable weight in complete silence until suddenly it fractures and fails without any warning. And producing it comes at an immense environmental cost. The global cement industry alone pumps out roughly 8% of all human-made carbon dioxide emissions every single year. We are trapped. Our entire infrastructure relies on a material that is structurally uncommunicative and deeply destructive to the environment. In 2004, two scientists playing around with a block of graphite and some ordinary Scotch tape made a discovery that eventually won a Nobel Prize. They isolated graphene. It's a flat, hexagonal honeycomb lattice of carbon atoms, exactly one single atom thick. Despite being virtually invisible, it is highly efficient at conducting electricity and easily stronger than steel. This sparked huge promises from the scientific community. We were told we'd soon have mobile phones we could fold like paper and batteries that charge in seconds. But 2 decades passed, and those predictions stalled completely. The problem was the math. Manufacturing pure graphene in large batches was incredibly difficult, driving the cost up to $100,000 per ton. You can't build infrastructure at those prices. Graphene turned into a running joke in labs worldwide, a theoretical supermaterial that was simply too expensive to solve any actual problems. The breakthrough didn't come from finding a way to make pure graphene cheaper. It came from researchers asking a different question. What if we took a lower-grade version of this carbon lattice and mixed it into the cheapest, most common material on Earth? It turns out you barely need any of it to see a difference. Imagine baking bread and putting just half a teaspoon of salt into 10 kilograms of flour. That is the exact ratio of powder going into a standard concrete mix. Because graphene is incredibly thin, a single gram can stretch to cover the surface area of 2 entire football fields. When you mix that into wet concrete, it weaves a massive microscopic web through the rough matrix of sand and stone. This web acts as a series of structural seeds, forcing the cement crystals to grow tighter and more organized. If a microscopic crack tries to form, it immediately hits this carbon barrier and stops. It works exactly like steel rebar, just scaled down a billion times, creating an internal maze that blocks water from seeping inside. To be absolutely clear with the data, this doesn't magically make the concrete 5 times stronger, but rigorous lab tests show it consistently delivers a massive 20 to 40% upgrade in overall strength and durability. A virtually invisible dusting of carbon powder is dramatically increasing the physical limits of humanity's basic building block. But strength is only half the story. Because graphene conducts electricity so well, weaving it through the mix transforms concrete from a dead, inert rock into an active sensor. This digital graph shows exactly how the mechanic functions. When a heavy vehicle drives over a graphene-infused beam, the concrete shifts microscopically under the pressure. As the physical structure flexes, the electrical resistance flowing through that internal web drops or spikes in real time. By continuously measuring these electrical shifts, civil engineers can actively monitor the health of a bridge. The concrete can report internal microcracks years before a human inspector could ever spot them with a flashlight. Our silent, static infrastructure is suddenly being wired with a central nervous system. Of course, all of these structural and sensory benefits are useless if the materials still cost laboratory prices. A massive workaround to the cost problem was developed at Rice University in Texas. Instead of relying on expensive chemical processes, they turned to high-voltage electricity in a method called Flash Joule Heating. Researchers found they could take carbon-rich waste, things like leftover coal, old tires, or discarded plastic bottles, and blast it with a massive shock of electricity for exactly 10 milliseconds. The intense heat vaporizes everything that isn't carbon, leaving behind highly useful, extremely cheap flash graphene. And this is where China is leveraging its massive coal reserves and unmatched industrial scale. They are actively pulling this process out of the lab and pouring this exact material into working highway projects. The financial barrier to a high-tech future was bypassed simply by turning the world's cheapest garbage into an affordable supermaterial. Let's look at this diagram comparing 2 structural pillars to see the environmental math. Because the graphene web drastically increases physical strength, Builders can reduce the overall volume of cement used in the right pillar without sacrificing a single ounce of load-bearing capacity. The data is clear. Adding just 0.1% of flash graphene into the mix allows you to cut the material's total carbon footprint by roughly 1/3. For heavy manufacturing nations actively building vast new megacities, this single material upgrade is a highly practical mechanism for hitting their 2060 carbon neutrality goals. But there are still significant engineering hurdles to clear. Dispersing that incredibly fine powder evenly through tons of wet sludge without it clumping together is notoriously difficult, and a few successful lab tests cannot perfectly guarantee how the material will hold up under 80 years of freezing rain and continuous traffic. If the industry can solve standardization in the mixing process over the next 5 years, this material will easily become the default foundation for our most demanding structural projects, from ocean tunnels to high-speed rail lines. We are taking the heaviest, silent building block in human history and using our discarded waste to wire it into an active, self-diagnosing network. The very ground beneath our feet is waking up.